All right, so at this point you would have done your homework check, and then we're going to do review 15 notes. So Ms. Stedman, make sure you pass out review number 15, and after the notes are done, you guys can either work on homework number 14 or sorry, 15, or ask questions from homework 14. So slope fields are used to approximate a curve given the derivative. So not every function in the world can you integrate. They have to be made a certain way for you to be able to integrate them. So slope fields are a way that if we can't integrate, we can't find the actual integral or antiderivative, we can at least graph slope fields and look at what the curve may look like. Just keep in mind on the AP test, if you're asked to do a slope field, you'll probably be asked to do 12 points. Just be really careful. Given those 12 points, make sure you check where the slopes are 0, which are your horizontal tangents, and make sure that you have them be horizontal. So the other one that you have to be careful about are undefined slopes, which can also be considered sometimes vertical tangents. And what I don't want you to do is actually draw a tangent line when the slope is undefined, okay? So just leave those blank. Other things that are really important about slope fields is anytime you're asked to analyze a slope field, if they give you a slope field and you're supposed to figure out which differential equation could match that slope field, then you really want to think of, well, where are your slopes 0? You also want to look at, are there any undefined slopes? And then figure out patterns to where the slopes are positive or negative. Looks kind of like a sign chart, but if they give you a bunch of options, then you can literally substitute in points and see will the derivative, because it'll be something like this. They'll give you a derivative set equal to some type of function over here. Let's make one up. Something like this. And you'll have a bunch of slope fields, and the way you can tell if this would be the differential equation to that slope field is you pick a point that's on the slope field, and let's say at that slope field you notice that the tangent line looks kind of like that, right? But if you substitute 0, 1 in here, it gives you a positive value. Therefore, this slope field automatically can't go to that differential equation. All right, separable differentiable functions. They're like the analogy or the answer to implicit differentiation. So this is used when your function is, or I shouldn't say function, your derivative is implicitly defined. So, let me see if I have an example. I believe I do. So, I actually want to start off with that basic example that we talked about. The given dy dt is equal to k times y. And I'm not even going to use k, I'm going to use a physical value in here. Let's do 2xy. So this will be our example problem. And I'm kidding, I don't want it to be t, let's make it x. So, a little correction. So this will be one example that I do want to try out. So remember, the steps for separable differentiable functions. First of all, this is what I mean by it's defined implicitly, meaning the variables are together, in a sense. So first thing you're going to do, separate your variables. So dy over y is equal to 2x times dx. Now we can integrate both sides when all the variables are separated. Now that I've done that, the left side, the integral would be ln of the absolute value of y. Right side would be x squared plus c. And I always put my plus c on the side with my x's. Next piece, I would need to use e to eliminate that ln. The absolute value of y is equal to e to the x squared, and then we can actually multiply it by e to the c. Remember, e to the x squared times e to the c. If you know that they have the same base, the powers can be added, and that's the rule I'm using to kind of undo that step. The absolute value can be eliminated by doing plus or minus, and I'm going to just rewrite this. So my e to the x squared is in the back. This guy, we just call that a. Call that a new constant called a. Okay? That would be the answer to that one. All right. Let's go through another example right here. That's number 2 from your packet. Ms. Denman, go ahead and press pause and let them work through the problem for a little bit. Give them maybe a minute or two, and then I'll go over the answer through the video. All right, so let me write down the equation here. I'll move that up, get that out of my way. So the equation is dy dx is equal to negative x over y e to the x squared. So first thing I'm going to do is separate, so I get y dy is equal to negative x over e to the x squared, and that's just, it's kind of odd to me. I don't like my e being in the denominator, so I'm actually going to move it up to the numerator, and it's a good habit to do that. So, oopsie, forgot my negative. So when you do that, it will actually help you out. So the right side is going to be a substitution problem. So u is equal to negative x squared du over dx is equal to negative 2x, and then du over negative 2x is equal to dx. So let's come over here. So I'm actually going to integrate the left side because that's easy to do. Y squared over 2 equals, and the right side, I'm going to rewrite the integral. So the pink integral would be rewritten as e to the u times negative x times dx. Oopsie, I forgot my dx right there. There it is. Dx, which would be du over negative 2x. So you'll notice that I pick up, change my color, I end up picking up this 2, and the negative x and the negative x will cancel. So I end up with 1/2 integral of e to the u du. There's no limit, so I didn't have to change my limits. The integral of that would be 1/2 e to the u, but e to the u, remember what u was? U was negative x squared, so I'm going to substitute that back in, and then plus c. All right, so things that I should understand. You see how the 1/2 was out here, and I decided to put my 1/2 out here? Then I would need parentheses around this whole entire thing. If you decide, which we can change it, if you were to decide to have your 1/2 stay with your e, then, oddly enough, let's see if I can erase this carefully enough, then I wouldn't need parentheses around this whole thing. And the 1/2 would belong only to the e to the negative x squared. So it does work out, and yes, the c does not have the 1/2. I'm going to go back to the way that I did it because I just want to show you what happens to the 1/2 times c. So remember how we were using that a? The a was for the constant, and because of this 1/2 times c, I could actually use a right there again. What do I mean by that? I mean that the y squared over 2 is equal to 1/2 e to the negative x squared, and I can call that 1/2 c, and I could just recall that a, something new. Going through, I'm going to actually erase this side of the board just so I have space and I don't have to change my screen. So I end up with y squared is equal to 2 times 1/2 e to the negative 1/2 or sorry, negative x squared plus that 2 got multiplied by that a also. So let me kind of show that one more time because I feel like I did that a little bit too quickly because I'm going to talk about that a again. So right here, I would multiply both sides by 2. This side by 2 and this whole entire side by 2. Alright, so when I do that, going back over to where I was, I'd have that y squared is equal to 2 times a half, cancel to 1, and then 2 times a, well, I can call that something new now. I can call it b. It's not necessarily wrong if you just keep a, but I like to show that I'm changing my constants. That's really the reason why I keep changing it. You really could just leave it as c, okay? It's no big deal. You could have left it as c here, you could have left it as c here, and you could have left it as c here. I'm just a little bit specific about it. Alright, so they want to know, this means that y has to be solved for, meaning y is equal to plus or minus the square root of e to the negative x squared plus my constant. And the point that I'm going to be using is 0, comma 2. First of all, that tells me that the y value is positive, so I have to use this guy. That's the first thing it tells me. And then the second thing, I'm going to use the point, e to the 0 plus b. 2 is equal to 1 plus b. 4, not plus or minus because I'm squaring both sides, not taking the square root of both sides. 1 plus b, therefore b equals 3. So the final answer would be, and I'm going to put that smack in the middle right here in red, square root of e to the negative x squared, and then plus 3, which will be this one. This one's number 6. Alright, so number 6, dy over y is equal to negative 2 dt. So notice I left the negative 2 on the right side. I do that because I just want to eliminate as much stuff on the side with y, because in the end I'm going to solve for y anyway. So ln of y, absolute value, is equal to negative 2t plus c. If y is equal to 1, t equals 0. So I'm actually just going to go through the process completely. Absolute value of y is equal to e to the negative 2t times e to the c. That y, to eliminate the absolute value, I use plus or minus. I'm going to rearrange this, put that negative back. And then I'm going to call it a. Oopsie. And then I'm going to use the point, 0, comma 1. 1 is equal to a times e to the 0. A is 1. So y is equal to e to the negative 2t. And when y is equal to 1/2, I would need to take the ln of both sides to eliminate the e. And t is equal to the ln of 1 over 2 all over negative 2. So that looks like an answer that's not up there. So we got to figure out why our answer is not there. And the reason is, remember, I'm going to just start out by putting the negative 1/2 in front here. The ln of 1/2, I'm just going to separate it like that so you can see it. So negative 1/2, ln of 1/2 would be the same as ln of 1, I'm expanding it, minus the ln of 2. Fraction or division expands to a subtraction. Ln of 1 is 0, so I get negative 1/2 times negative ln of 2, which the negatives will cancel, and I will end up with an answer of ln of 2 all over 2. All over 2, which is this guy. And last one. This is just to reiterate, I'm not going to do this whole problem, but just to reiterate the fact that not every problem is an ln problem, is why I wanted to show this one. This would be y to the negative 2 power dy is equal to 2 dx. So this would just be a normal power rule. Add 1 to the power, divide by that power equals 2x plus c. Okay? Another reminder is, how do you know that it's an ln problem? Ln problems in general are going to be functions that are in the form of, and in terms of implicit differentiation, they'll look like linear functions. So they have to look like this, or the other way. I could show you f of x is equal to 1 over ax plus b. So these are all, they're going to be ln. If I want to take the integral of these, they become ln functions. What wouldn't be ln, so examples would be dy over 2y plus 5. That would be an ln. What wouldn't be an ln is the second that I do this. That is no longer an ln. Or if I was to do something like that, that would not be ln. Has to be linear. And not only linear, to a power of 1. That's how you know it's an ln problem. All right. This guy would be an example of one of the free response questions that you have to do. I don't remember if I assigned it for a homework problem, but I wanted to highlight from chapter 6, when you guys took your test, a lot of you got this part completely wrong, describing all the points where the slopes are positive. Slopes are positive, not for these 12 points, so you're not supposed to list a bunch of points. You're supposed to figure out how could you make this positive. Well, let's think about the fact that this piece is always positive, so we don't need to worry about it. So therefore, you're only looking at y minus 1 greater than 0, y is greater than 1. Those points where your y value is greater than 1, that would be where the slope field has positive slopes. That's the only piece I wanted to do with that guy. I think that's it.